So good evening, everyone. My name is Hanami Nara, and I'm a faculty at the University of Texas MD Anderson Cancer Center and a board member of AAASE, the Asian American Academy of Science and Engineering. It's my great pleasure to welcome you all to the AACE Distinguished Lecture that will be given today by Professor David MacMillan. To begin our program, I would like to introduce Professor Mohan Shankaran, who is an AACE board member and professor of engineering at the University of Illinois at Urbana-Champaign.
Thank you, Dr. Nora. Hello, everyone. I'm thrilled to introduce AAASE today on behalf of the president, Professor Yiguang Zhu, and my fellow board members. Today is the second distinguished lecture that AAASE or AACE has organized. For those of you that joined our first lecture a few months ago, I would like to welcome you back. For those of you that are joining for the first time today, I want to spend a few minutes telling you about AACE. AACE is the Asian American Academy of Science and Engineering. The mission of AACE is to advance leadership and excellence in science and technology in the United States and to advocate for the voices and rights of Asian Americans and Pacific Islanders. Asian Americans are a very important and growing contingent in the US. Currently, there are 22.4 million Asian Americans, which is 7% of the total population, and this is expected to more than double to 46 million by 2060. Our organization provides an opportunity to share our diverse but often common experiences, bring to light our incredible achievements, and create a voice that will ensure sustained and growing opportunities for our future Asian American generations. At AACE, we are already investing in that future. We are organizing a summer academy for high school students, which will take place this June 22nd to 26th at Princeton University. There will be lectures on AI, robotics, data science, green energy, and many more topics. In addition, we have created an early career board made up of those in the early stage of their professional career. I want to take the opportunity to introduce you today to those members. They are Cheyenne Tang, Kim Cheng, Kyler Zhu, Akane Wang, Sean Wu, Lin Han Shen, Hannah Lee, Christina Liu, and Alex Chen. As you can see, many of them are here today. I want to thank all of you for joining us today, and we look forward to continued interactions in the future. And now I'm going to hand it back to Dr. Nora.
Thank you, Professor Shankaran, for your introductory remarks. It's now my great honor to introduce our esteemed guest, Congressman Andy Kim. Congressman Kim represents the 3rd Congressional District of New Jersey. He's the son of Korean immigrants, a Rhodes Scholar, a trailblazer, and a proud father. Please join me in welcoming Congressman Kim for his opening remarks.
Thank you so much for giving me an opportunity to be with you all here today. I'm so proud of the work that AAASE does, and to be a part of this effort. You know, now more than ever, we need to make sure that we're raising up the work that Asian Americans are doing around this country, highlighting it, building that community for them to be able to engage with one another and really be able to take their work to the next level. I am somebody that has been a son of a scientist my whole life. It was science that brought my family to the United States. My father came here from South Korea to do a PhD. He did a PhD in genetics here in the United States, and that's what gave our family the opportunity to be able to be here. It was science that gave my father the job that allowed my family to be able to live in New Jersey and raise us here, give us the kind of life that we wanted, while also giving my father the opportunities to be able to pursue science, to pursue his intellectual curiosity, to try to solve the problems of our time. And it's something that I've always had a great respect and esteem for. For me, I now am in a position as a member of Congress representing my home district in New Jersey, the district that gave my father those jobs and those opportunities. I now am trying to do my best to make sure that we are empowering all of you, giving our researchers, our scientists, our engineers the kind of platform that they need to be able to do their research and continue to allow the United States to be cutting edge in terms of our leadership globally when it comes to these types of pursuits. I'm also trying to dedicate my time and my effort and our country's efforts to be able to lift up a new generation of students to be able to study STEM, to be able to engage in the work that is so badly needed to continue to allow us to take on these new challenges that we're facing. It's not lost upon all of us that we face some great challenges up ahead. We are living at an inflection point in terms of technology, in terms of science, and that some of the biggest challenges that we face as a globe are ones that we're going to need to harness the best of us to be able to do the work needed to be able to solve these problems, come up with these solutions. And I'm very excited that we are making those investments. I'll always try to be able to fight for more, be able to get you and so many others the kind of work that they need. So I just want to say thank you so very much. And I'm so honored as well to be able to be here as part of the effort to introduce Professor MacMillan. I've never had the chance before to be able to introduce a Nobel Prize winner. So I'm very excited about that, but also someone from my home state here in New Jersey. I'm so proud of the resources that we have in New Jersey at Princeton and other institutions. And around this country producing so much great scholarship and work. So thank you again for letting me be a part of this. I just wanted to show my solidarity and support for all of you in working together and lifting up science and engineering, but also lifting up the Asian American community around the country. Thank you, everyone, and take care.
Thank you, Congressman Kim, for your inspirational opening remarks. I would like to now introduce our co-sponsor attendees. Firstly, Ms. Akane Wang of the Princeton University Asian American Students Association, Professor Kai Li of the Asian American Scholar Forum, Professor Ling Shang of the Association of Chinese Americans in Cancer Research, Professor Michael Harold of the American Institute of Chemical Engineers, and Dr. James Tsao of the New England chapter of the Sino-American Pharmaceutical Professionals Association. I would like to thank all the sponsors for their support of the AAASE Distinguished Lecture. So to begin the lecture of our distinguished speaker, I will now turn over the podium to Dr. Fei Xu. Dr. Xu is a renowned leader in the pharmaceutical industry with over 20 years of experience in cancer drug discovery and clinical development. Among her many accomplishments, she played a pivotal role in the development of 3 FDA-approved cancer drugs. Dr. Xu is currently the Global Biomarker and Diagnostic Director at Novartis Oncology and will serve as the moderator for our program.
Thank you, Dr. Nora. Good evening, everyone. Today, we are very fortunate and honored to have Professor David MacMillan come to our platform to speak to us. Professor MacMillan started his career as an assistant professor at UC Berkeley. In less than 5 years, He became an endowed chair professor at Caltech. In 2006, Professor MacMillan moved to Princeton University, where he was an endowed chair professor and the director of the Merck Center for Catalysis. From 2010 to 2015, he was the chemistry department chair. And since 2011, he is the James S. McDonald Distinguished University Professor. And as you all know, last year, Professor MacMillan was awarded the Nobel Prize in Chemistry for his seminal work in the development of asymmetric organocatalysis. Besides the Nobel Prize, he has also received more than 25 major chemistry awards. Importantly, over the last 21 years, Professor MacMillan has trained 57 PhDs in chemistry and more than 170 postdocs for the pharmaceutical industry or academia. And using his deep knowledge and expertise, Professor MacMillan has been serving on scientific ad board or as consultant for more than 15 major pharmaceutical and biotech companies. He also has founded his own 3 biotech companies. Now, it's my great honor and privilege to introduce you 2021 Nobel laureate in chemistry, Professor David MacMillan.
Wonderful. Well, thank you, Dr. Sue, for that very kind introduction. I feel incredibly privileged to be given the opportunity to present for this AACE meeting. The Asian American Academy of Science and Engineering, you mentioned that there's so many PhDs and students who came through my lab, and so many of those have been Asian Americans, and I've been extraordinarily fortunate to be the beneficiary of working with so many fantastic people. I was going to give a talk today, which is going to touch a little bit on my background of how I got here in the first place, in terms of my own, basically my own life, my own pathway. Tell you a little bit about the development of sustainable catalysis and asymmetric organocatalysis. And then maybe for the last 5 minutes or so, for a little bit of fun, I thought I'd tell you a little bit about what it's like to win a Nobel Prize, because I always find people find that part just as interesting as almost any other part. So hopefully you all too. Okay, so who am I? Where am I from? You might be able to tell from my accent. I'm from Scotland. Scotland, if you think about the UK, that's the very top part. It's a large landmass, but population-wise, it's a lot smaller than England. But I think we certainly punch above our weight. At least I like to think so. I grew up in a really tiny town that's called Belsill, which is just outside of the city of Glasgow, which is in Scotland. And it's a really working class neighborhood. I grew up as a working class kid in Scotland, but an incredibly happy kid, an incredibly happy upbringing, great time. The people there were really wonderful. I always love to show this map because Americans, when they go to Scotland, they always visit Edinburgh. They never go to Glasgow. So I always like to sort of give an advertisement for go to Glasgow, and it's an amazing place. It's a really fun place. People have a great sense of humor. And I always like to show my home. This is where I grew up in Scotland, and this is called a council house. And a council house is a state house, meaning when you can't afford your own home, the state provides you with a home, which was a really fantastic system that was provided as being part of Scotland. I always enjoy showing this picture because often Americans will ask me, why are you only showing half the house? But that's the only part that we owned, was that left-hand part. That was where our house was. So after I won the Nobel Prize, the Nobel Foundation asked me to provide some pictures when I was a kid growing up. And these are some photographs which are now on the Nobel website. And I actually didn't have any photographs of myself So to ask my sister to send some to me. And so these are the pictures, but I've always got this kind of slightly scared feeling that that picture on the left-hand side of the baby is actually my sister. And this is like the greatest practical joke of all time, that her photograph is on the Nobel Foundation website. But this is just this traditional family pictures in Scotland. Here's us at the beach when we're kids. And this is me as a young kid outside my back door. I had a very traditional Scottish upbringing, as I said, very working class, but it was incredibly happy. It was just full of humor, full of people, really enjoying themselves. But when I was young, this is a photograph of my brother. He's older than me, and he decided to do something that was quite remarkable. And what it was he decided to go to college. And the reason why this is remarkable, to myself and everyone I knew in the town where I lived, we didn't know anyone who'd ever gone to college or university before. People just didn't do that. And in fact, my mom and dad were quite upset with him because they thought he was just trying to be lazy and avoiding getting a job. But he was determined, and he went off to university. And after being at university for 4 years, he graduated, and this is a photograph of him graduating, with a bachelor's degree in physics, which was wonderful. Now, the most important part of this for me was the day he graduated, he actually had a salary that was more than my father made. My father was a steel worker and my mother was a maid, and his salary was more than their combined salary. And at this moment, I think a light bulb went off in my mom and dad's head, that at this moment, they decided that I had to go to university. That was, the decision was basically made for me. So I was very fortunate that my brother decided to do this. So this is me. I went off to college. You can tell this is the 1980s just by looking at my hairstyle. I've got that huge poofy 1980s hairstyle. And I went off to do physics. I went off to do physics because I was told that my brother had a bachelor's degree in physics. So I was told I should do the same thing. But after a year doing physics, I realized I really didn't like it. I didn't enjoy it. I didn't have much fun with it. So I decided I had to do something else. And the something else I decided to do was actually go off and do chemistry. And in my second year of doing chemistry, I sort of fell in love with organic chemistry. And I started to realize it was a subject that I really thoroughly enjoyed doing. And for me, this was a great lesson in life at that moment, is to follow what you love, to follow what you do and not necessarily follow what people think is the best pathway for you. Again, this is my class in the 1980s. You can tell, again, it's the 1980s by the big hairstyles. This was just a fantastic group of people to basically grow up with and receive a great education with. So at the time, I decided, and when I graduated, that I really wanted to move to America. And I wanted to do a PhD. And I wanted to move to America because, to be honest, I really love sports. And the NFL had become really big in Britain, and I decided I really wanted to come to America to see the NFL. And I applied to 18 different universities in the States to try and come to get a PhD. And I wrote letters to 18 people and basically received 18 rejections. And I was about to give up, and I wrote my 19th letter. And the person there wrote back to me and said, look, you can't be accepted into a PhD program just by writing a letter. And he actually sent me an application form, which I filled out and was accepted, and was accepted into UC Irvine in Southern California, where I moved to as a 21-year-old from Scotland. I moved to Southern California. And it was a really remarkably fantastic time, learning about what it's like to be an American, learning what it's like to be in Southern California. I remember going around the first apartment complex I had, and the lady was showing me around, and she showed me the tennis courts and the swimming pools, and she pointed out to me, these are the jacuzzis. And I remember asking, what's a jacuzzi? I'd never heard of a jacuzzi before. And she told me that's a place you go to relax, which I thought was really just fantastic. Anyway, so that's basically my path of how I came to America. I'll come back to this in a few more moments. But I wanted to sort of leap forward in this story and talk about what happened at the end of last year. On October 6th, I was very lucky enough to win the Nobel Prize for this thing called asymmetric organocatalysis. And I want to jump forward to this part. You'll understand why. We'll move back to that timeline later on. But since I've won the Nobel Prize, I've been asked a lot of different questions by a lot of different people. But probably the number one question that people ask me is asymmetric organocatalysis. What on earth does this mean? So what I thought I would do is I'd try and break this down in a least technical way possible and hopefully make some sense of this. So the first question is, what is catalysis? To describe catalysis is actually not that difficult. This is a picture of my office. You can see some of it behind me. But this is my office. And if you look around you right now, absolutely everything around you is made from a chemical reaction. Absolutely everything. In fact, if I look around my office, all of these different materials, all of them made from a chemical reaction. If I hone in on one of them, this chemical reaction here, this is the chemical reaction to make caffeine. Caffeine is the key chemical that's in coffee. It's the stimulant that's in coffee. And it turns out these chemical reactions, almost all of them require energy for them to happen. Almost none of them are spontaneous. Now, if you think about how these energies for these reactions work, and this looks quite technical, and I promise you I won't make it so technical, but this is a sort of way a chemist would represent the energy involved to make caffeine. Now, the way I like to teach this to undergraduates or high school students is imagine that every day you're walking home, and to get home, you have to walk over a pretty tall hill. That would obviously require a good amount of energy every day to sort of get home. So what catalysis is the equivalent of building a tunnel through that hill, such that you would expend a lot less energy for you to get home every night. And that's exactly what catalysis does for chemical reactions. It makes chemical reactions easier, makes them faster, and it actually allows many reactions that were previously impossible to become possible. So you might ask, well, how does catalysis really impact the world? Or does it impact the world? And it actually impacts the world in a lot of really interesting ways. This is one of my favorite ways to show this. So this is the population of the world over the last 2,000 years. And you can see it's pretty stable over 2,000 years. And then at the beginning of the 20th century, there's this inflection where it jumps up very sharply to 8 billion people. Well, it turns out you could not have 8 billion people on this planet. It would not be sustainable without this one catalytic reaction, which is shown here, the conversion of nitrogen over to ammonia. So you might ask yourself, why do we need this catalytic reaction? And it's really simple, because you need ammonia to make food, and we simply wouldn't have enough food on our planet for 8 billion people without this one catalytic reaction. What I find is a sort of really interesting trivia that comes out of this. If you actually think about your body right now and all the proteins and enzymes and DNA that's in your body, and think of all those nitrogen atoms which are in all of those materials, 50% of those nitrogen atoms actually come from this one catalytic reaction which is performed in a factory. Other ways that catalysis is very important, 90% of industrial scale chemical processes right now use catalysis, and 35% of the world's GDP is based upon catalysis. And that number is only going to keep increasing as we move towards more and more sustainable processes. Some other ways that you might find interesting, we already talked about the conversion of nitrogen to ammonia. Turns out for medicines, you use catalysis every single day. For solar cell materials, renewable energy, you need catalysis. Materials, polymerization, every single day is reliant upon using catalysis. So clearly, catalysis is important. So the second part about this is, what about asymmetric? What does asymmetric mean? So that sounds like a pretty technical term, but it turns out it's really easy to understand asymmetric. If you actually look at your hands right now, you just sort of put them side by side, and you can ask yourself, are they asymmetric? The easier way to ask that question is, are these hands identical? And it turns out they're not identical. They're actually very similar, but they're mirror images of each other. Now, we know they're mirror images because if you take your left hand glove and you actually try to put it on your right hand, we know that doesn't work. You know, your glove does not recognize the hand. So that tells you that they're similar, but they're different. They're actually asymmetric. So the reason why I'm telling you that is it turns out that organic molecules, these molecules that we work with, have this same property. They exist as mirror images. So these mirror images are really interesting. They're similar, but they're different. Now, if I was to go into a lab and try and tell them apart, I would have to use a really expensive piece of equipment. This equipment is roughly about $60,000, and it would take about 20 to 25 minutes for this instrument to tell these two molecules apart. For chemists, what we find really interesting, though, is if you were to take those same two compounds, and this is a photograph of my daughter when she was just 3 years old. Even my 3-year-old daughter, she could tell these two compounds apart in literally nanoseconds. And she can tell them apart simply by smelling them. She can actually smell the difference between these two mirror images. So you might ask yourself, why is that? Why is it so difficult to do in a lab, yet a human being can do it so readily? Well, this comes down to the fact that all of life is made up of molecules which are predominantly one mirror image, but not the other mirror images. And much like the way the glove can recognize the hand, the human body can recognize the differences between these mirror images that you were exposed to. So that has some really interesting implications if you think about it. So instead of thinking about these mirror images as being your hands, think about medicines. Medicines, in many, many cases, exist or can exist as mirror images. And while one mirror image can be recognized by your body in a very positive, favorable way as a therapy, the other one can be detrimental, it can be harmful, it can be toxic. And as such, it becomes really important that you can make one of these mirror images without making the other one. So the question is, how would you do that? How would you make one mirror image without making the other one? Well, obviously catalysis. Makes a lot of sense to use catalysis to do that. And the question of being able to make one mirror image without making the other one, that's now known as asymmetric catalysis. Okay, so we got those two parts. Then the third part becomes, what does organo mean? What does that come from? Well, I'm going to take you back to my part of the story, back to 1996, when I told you I was at Irvine, I'd moved to Irvine. And asymmetric catalysis in 1996 really had two branches. There was just two ways of doing it. The first way was using biocatalysis. That's using these catalysts that exist in our body, these large enzymes, and using these enzymes, you can indeed make these mirror images selectively. The second way of doing it is a man-made way of doing it, and that's to use metals. Metal catalysis can also be used to actually make these single mirror images. And in 1996, I left UC Irvine. I moved across to the East Coast to Harvard to do a postdoc. And I did it to join the group of this man. This is Professor Dave Evans, one of the most influential, most successful chemists of the last 3 decades. And Dave and his team have become masters in this world of being able to make these single mirror images. And I learned a lot from Dave and his team because they worked on using metals. They used a lot of metals to actually do this selective production of these molecules. And this was a really fantastic time. I learned so much. But at the same time, every single day, I would have to work in this contraption for many, many hours. And for those of you that don't know what this is called a glove box. And a glove box is simply a box that doesn't have oxygen, and it doesn't have air, and it doesn't have moisture inside it. And the reason why you had to keep a lot of the chemicals in there is because they would be too reactive to exist in our outside environment. So as a result of that, you'd have to stick your hands in this thing and work in it every single day for hours and hours and hours. So after 2 years of doing this, I have to be honest, I started getting a little bit fed up about this. And I started to think, why are we spending so much time in these glove boxes every single day? So to think about this in a more straightforward way, this is the typical catalyst that we would use. And I hope you can see this, but you can actually separate this right down the middle. And on the right-hand side, we have these things called metals. Now, metals are often expensive, toxic, or difficult to work with. Not always, but many of them can be. And they're not sustainable, meaning once you pull them out of the earth, you can't really put them back in again. But what's interesting, if you actually look at the left-hand part of these catalysts, they're actually built up of not metals, they're made of organic molecules. And these are the molecules of life, and they're typically inexpensive, they're safe, they're sustainable. And so at this point, I started to ask the question, what if we could, instead of using these metals, what if we just use the organic part to do all of the catalysis? And this eventually became known as organocatalysis. So in 1998, I landed a job as an assistant professor at Berkeley, and I moved over to Berkeley. This is a picture of myself in a very young group, just getting started at Berkeley. And I really love this photograph because it's 10 past 10 on a Friday night, and we're all in lab, trying hard, trying to make a difference. Now, in terms of what we decided to work on, I knew what we wanted to work on, which was organocatalysis. And the reasons seemed obvious, at least at the time. The idea was we should be able to make all of these catalysts from nature's building blocks. Because they exist in life, the way organic molecules in our body exist in life, which is out in the atmosphere, they should not be sensitive to water. They should not be sensitive to air. Because they're so abundant, they should be really inexpensive. You shouldn't have to operate within these glove box contraptions when organic molecules are happy out in the atmosphere. And the last part is they're completely sustainable. They're recyclable. As soon as you've used these catalysts, they'll go right back into the life cycle. But this was not the original reason I was most excited about this idea. The original one was the idea, could you actually use these catalysts not to perform one chemical reaction, but could you actually use them to perform lots and lots of reactions? And maybe this would become a field of research. Now, that was a pretty grandiose idea. And the only problem was I had absolutely no idea how to do it. No idea well, I knew I wanted to do it, but I had no idea how to. So, but fortunately, one day in their first year, I was in lab, and one of my first year graduate students called Tristan Lambert, this is him shown here. He's now actually a very successful professor in his own right over in Cornell. But as a first year graduate student, he came up to me and asked a very simple question: what is the mechanism of reductive amination? This was a great question. As a young professor, I ran to the board to try and explain this to him, and I wrote it down. And as I wrote this down, I wrote down, well, he'd taken what's called a carbonyl and an amine, and it reversibly, it goes back and forward from forming an aminium ion. And it's only when it's in that right-hand molecule does it have the correct electronics to go on and do the subsequent chemistry. And it was right there, right then, that I had the quintessential eureka moment, because I suddenly realized, wow, you should be able to do this or use this to do organocatalysis. Because if you could condense these with alpha, beta, and saturated aldehydes, this looks exactly like a field of catalysis that had been around for a really long time using metals. To sort of write that in a slightly more conventional way, the equation on the top line had been used for hundreds of chemical reactions. But the one on the bottom, using the organic molecule, there's absolutely no examples of. But if these were really simultaneous equations, that means organic molecules should be able to perform hundreds and hundreds of chemical reactions. At least that was the idea. Okay, so we had to pick a reaction to test this on. We decided to go for one of the sort of most famous in the whole world. This is the Diels-Alder reaction. It in and of itself won a Nobel Prize deservedly for Diels-Alder in 1950. Very powerful reaction, allows you to make these really complex molecules from really simple ones used extensively for medicines as well as materials. So we decided to test this. This is actually the notebook page of a first year graduate student, Kateria Rent, the first time we ever tried this. And I hope you can see the arrow there. And above the arrow is the organic catalyst. So we performed this reaction. And if you scroll all the way at the bottom of the page, and I hope you can see this is highlighted here, it says not racemic, not racemic. What does that mean? Well, that means not racemic means it makes one of the mirror images in a larger amount than the other one. That was extraordinarily exciting. I remember walking into my office, closing the door, jumping up and down for 5 minutes. I remember calling my wife and telling her, I think I'm going to get tenure. We're so excited about this whole thing. But when my feet came back to the ground, I realized the part at the top where it says initial result 48%. What does that mean? Well, it turns out if the chemistry community was really going to take this seriously, that number was going to have to be about 90%. So at this stage, we're faced with a question: do we publish this initial result, or do we go for the gusto and actually try to get this up to 90? We decided to go for the gusto, and I can tell you the next 6 months was some of the most nerve-wracking 6 months of my life, worrying that we were going to get scooped on this idea. But we eventually came to this catalyst shown on the left, and without going into great detail, one of the things we loved about this catalyst is it's actually made from phenylalanine, which is the sweetener you'll find in Equal. It's an amino acid. And it's also made from acetone, which is paint strip or nail varnish remover. So this is a really, really inexpensive catalyst. But the reason why we really, really liked it was because now these jumped up to 90% in terms of the mirror images, which was really exciting. So now we had to publish this manuscript. And as a young professor, you want to sort of climb to the highest rooftop and scream about how great this was. And I really love going back and reading our first paper on this, because you can sort of feel that sort of emotion. The first part was we actually invented this word, organocatalysis. And you might ask, well, are names important? What's in a name? Well, names are really important, especially in science. And I'd love to highlight this this is Jan Jacob Berzelius. He's a Swedish scientist from the 1800s. And he actually invented the term catalysis, as well as the term protein, polymer, isomer, organic. He invented all of these terms. And what's really important about this is it gave chemistry lots of identity using new types of vocabulary. And this tradition of using names in this useful way carried forward into the modern era. Things like machine learning, AI, nanotechnology, organocatalysis, they provide a really nice umbrella for areas or fields to effectively grow beneath them. But beyond that, the second thing we did was we introduced the concept of what we call a generic activation mode. That sounds like a very complicated term, and it's not. All it means is we introduced the idea that this should work, not for one chemical reaction, but for many chemical reactions. So we set off to test that, and we tried it. And they went, that was the first one I just showed you. They went bang, bang, stop. It sort of ran out of gas really quickly. So that was really disappointing. But this happens a lot in science, where you get a nice proof of concept, but the first catalyst is not going to take you the whole way. So at this stage, I was really fortunate at two wonderful young graduate students in my group who performed what I would call molecular engineering. And by molecular engineering, all I mean by that is on the catalyst on the top left, they took away 2 carbons, and on the one on the right, they actually introduced 4 in a slightly different shape. And the idea with this precision change is you're trying to have this really beautiful outcome. And to non-chemists, especially the ones in Europe that I talk to, I always love to show this in terms of soccer. Soccer is one of my favorite things in the world. This is Zlatan Ibrahimovic, who's a football god. And I always love to show this goal, because this is a soccer goal. He scores from 40 yards out, which is just spectacular. And it's an absolutely beautiful piece of precision athleticism with a beautiful outcome. And we were trying to do exactly the same thing, by actually using a catalyst. So we took our new catalyst, and remember, originally we had 3 reactions. And when we started with our second generation catalyst, now we were off to the races. And really, fortunately, other scientists, Jorgensen and Hayashi, came along, and they introduced another catalyst, and this amplified the whole thing to an even larger extent, which was really, really exciting for us. Okay, so what other things can be enabled with organocatalysis? And really briefly, I won't spend really much time on this at all. It turns out that nowadays, what we're doing with this is we're actually using all the lessons we've learned from harnessing sustainable solar energy to sort of power the planet. We're now using that towards also chemical reactions for making materials or making medicines and lots of other important sort of substances. And this has become a field in its own right. It's become known as photoredox catalysis. And I love showing this video because the colors are just amazing. It sort of looks like these beautiful sort of Frankenstein labs with all these really great chemical processes taking place. Okay, so what are the applications of what can you actually use it for around the world? And there's many different applications. I'm just going to show you a couple. One of the ones, which I think is really interesting, is it turns out that all of the companies that make perfumes and fragrances and flavors now use organocatalysis extensively. And that doesn't sound so substantial until you realize the amount of material that's made in terms of perfumes, fragrances, and flavors on a daily basis around the world. And the energy reduction and the cost reduction by doing this is really significant. In fact, there's this one process which is now performed in India on a 400 metric ton scale per year, is performed using exactly one of our types of organocatalysis. In terms of materials, you've probably heard about this huge problem we're facing in terms of plastics polluting the whole ocean and plastics polluting everywhere on Earth. And Bob Weymouth and James Hedrick are now using organocatalysis to effectively take polymers and break them back down to monomers using organocatalysis, which then allows you to take those monomers and take them right back to polymers again. The great news about that is that allows you to make the whole polymer economy completely recyclable using this type of chemistry. But without question, the #1 application for organocatalysis has been in the production of drugs. I'll show you one example. This is just one from Merck. This is talsegipant. As you probably know, migraines are suffered on an enormous scale all over the world. And this molecule is one where you can make one of the desired mirror images using this type of catalysis that we invented at the earlier part of this story. The one last part I'll point out, and this is something that I'd say I'm very proud of, but I can't admit to the fact that we saw this coming. This was a bit of a surprise, but it was a really positive surprise. This is something we call democratizing catalysis. And what this means is this type of catalysis is extremely inexpensive because it's using these abundant materials that are everywhere on Earth. And as a result of this type of research is now being performed on every continent and basically all countries around the world, regardless of the resources they have, either to teach people or to perform new types of research. So when people ask me, where are the next big ideas in organocatalysis going to come from? I always say, I don't know, but I know that it's not going to be based on who has the most money, who has the most funding. It's going to be based on who is the best idea. And that to me is something that is very close to my own values and I think is really important. Okay, so what does the future hold for organocatalysis? Quite frankly, I don't know. I don't like to predict the future too much. But one of the things I will tell you that as we move forward, we have to become even more sustainable in how we perform catalysis if we're really going to support the continued growth and population of our Earth. And that means we have to get behind things like organocatalysis, biocatalysis, photocatalysis I talked about, as well as electrocatalysis. These are all going to become more and more prevalent as we move to towards a more and more sustainable future. All right, so I was going to, that was the last chemistry slide. I was going to take the last 5 minutes, if I have time, just to tell you a little bit about what it's like to win a Nobel Prize, if we have time for that. And tell me if we don't. If we're running low on time, I'll be happy to stop. But I thought one story I'd tell you, which is another question that people ask me all the time, is how did you find out? How did you find out you'd won this? And I kind of enjoy telling this story. I think it's a funny story. And it's funny because on October the 6th of last year, I was lying in bed and my phone started buzzing at the side of my bed. And I actually usually wake up easily, but I didn't that morning. It was about 5 o'clock in the morning and my wife jumped out of bed and she started getting really mad with me because my phone was buzzing. So she took my phone and moved it onto the window ledge away from me so that I couldn't hear it. But as she sat down, she said, you know, you've got a couple of texts from some people. I'm not sure who they're from. And I got up to sort of quickly check them. And the first one is it says, Dr. MacMillan, please call me Goran Hansen, Royal Swedish Academy of Sciences. And I'm looking at that going, Dr. MacMillan, who's Dr. MacMillan? That's not a Scottish name. So I was like, this is someone I've really no idea who this is. And then I also got a text from the other recipient, the other person who won this prize, Ben List, and it says, wake up. So I decided to call him. He tells me what it looks like we've won this prize. And I really didn't believe him. I told him, I think this is a complete practical joke that's been played. But I've had a lot of really mischievous but fun graduate students over the years. I was pretty sure this was a great practical joke. So I told him this. I said, I received a text from someone in Sweden. They spelled my name wrong. I'm pretty sure this is people who are playing a prank. And he says, I tell you, that's a pretty good prank. I know the voice of the people, Dave, this is happening. And I told him, I bet you $1,000 it's a prank. If they were trying to reach me, I'm pretty sure they would have my number and my actual name. Sorry to let you down. At that point, he says, well, call me when they reach you. I look forward to the $1,000. That's going to be a nice bonus. Dinner together. And I wrote, no, going back to sleep. Cheers. And that's exactly what I did. I went back to sleep. So I went back to sleep for about 20 minutes, 25 minutes. Then I started to wake up, decided I would go downstairs to see, look up on the web to see who won the Chemistry Nobel Prize. And I went downstairs and opened up my laptop and looked up the New York Times. And when I looked up the New York Times, basically what I found was this photograph or this artist's impression. Now, the person on the left-hand side, I think, looks somewhat like Ben List, but the person on the right-hand side, I had no idea who this was. So I'm sort of looking at this, trying to figure out what's going on, and then I read my name at the very bottom. And people always ask me, what was my emotion the moment I realized I won the Nobel Prize? And I said, well, it's both sort of elation and slightly offended at this artist's rendition that this was supposed to be me, because this is this very weird moment. I sort of realized the world was going to see this. But it was an amazing day, and it kicked off very quickly. My group had an amazing time. This is, as I think it's really early in the morning. I think it's 10 to 10. There's actually no place in Princeton you can buy alcohol at that time in the morning. So I have no idea where they got the alcohol from, but the party started right at that moment. And very quickly, the university started having parties all over campus, which was amazing as well. Really was truly wonderful. Your world sort of changes in a moment. For example, that day I did many interviews, the New York Times, Wall Street Journal, BBC, many TV stations all over the world. I was on BBC World live that night, actually, to the whole world. And it's kind of weird when on a Tuesday, you can hardly get your kids to talk to you. And then on the Wednesday, you're talking to the whole world. It's a very sort of strange sort of sensation. And you also get to hang it. These are all some of the Nobel Prize winners at Princeton, and they come and sort of celebrate with you, which is kind of wonderful. Now, we didn't go to Stockholm to receive the prize because of COVID. They're actually going to hold the ceremony this year, but they did bring us down to Washington, D.C. And this is me with my family, my daughters, on the left-hand side. And on the right-hand side, this is my family again. But this is my sister and my brother, who also came over to be part of the celebration, which was a really amazing day. And if there's time at the end, I'll tell you a funny story about my Scottish kilt, which I'm wearing. I don't think I have enough time to tell you, but if anyone's interested, I'll tell you later on. It was very funny. Anyway, so one of the other questions people always ask you is, who have you been able to talk to? Who do you get to meet? And it is just incredible, like the people you get to meet. And I'm going to not go through them all. There's just too many, but you get to meet lots and lots of great people. So this year, I mean, it's interesting. This weekend, actually, I'm flying over to Korea as a guest of the newly elected president to meet with him, President Yoon, who's asked me to come over for the inauguration, myself and my wife, who is Korean American. And we're flying over for the inauguration. Then we're going to sit down and talk to him. He wants to talk about science policy, which is great. I'm going down with the other laureates to meet Joe Biden, also later in the year. And in about 4 weeks' time, I'm actually going over to have dinner with Nicola Sturgeon, who's the First Minister of Scotland. So you get to meet some really fantastic politicians. And actually, Senator Chris Coons has asked me to join a committee down in DC as well, which is to do with the climate situation. And I'm really feel very fortunate to be part of that. And that's all wonderful. But you also get to meet some other really interesting people. And maybe Congressman Kim will recognize this gentleman. This is actually a few years ago, to be honest. But this is Jay Lee. Jay Lee, as you probably know, is the chairman of Samsung. His father created Samsung. And he actually invited me over in his house with all my family. And I love this picture because in Korea, Jay Lee is like the royal family, and his house is just incredible. But the other reason why I love this photograph, on the very far left is my mother-in-law. And she's an amazing woman, but she's a tough lady. And she's really, really hard to impress. And she's never really been that impressed with me, to be honest. But on this day, she's basically in the house of the royal family of Korea. And if you look closely, she is almost smiling, which I find absolutely fantastic. I really, really love this photograph. Other people you get to meet, and I won't go through it in great detail. Some of you may be soccer fans, but this is Sir Alex Ferguson. He's the greatest soccer coach ever. Coached Manchester United for many, many years. And last week I was down in Manchester hanging out with him and having dinner, which was one of the greatest moments of my life. And then I'll tell you one other quick story and then I'll finish off. But you meet some really remarkable people. So this is obviously the Spock and Captain Kirk. And just after I won the Nobel Prize, actually, William Shatner, who played Captain Kirk, called me up and said, could he interview me for a show he does from LA? And I said, sure. So I was on with him and we had a great chat for half an hour. Then we actually stayed on chatting afterwards. And I thought it was a really good conversation. And then afterwards, his assistant called me up and said, can he call you up now and again if he has questions? I'm like, sure, you can call me up. And this is one of the things you find out when you win a Nobel Prize. People assume you know everything, which is clearly not true, but it's a kind of amusing aspect of the whole thing. But anyway, so this is one of the bizarre things is that Bill Shatner calls me up all the time now and we chat by Zoom. And one of our more recent meetings, he actually called me up and said, David, what is a photon? And I love this because Captain Kirk is asking me what a photon is. This is a sort of really fantastic, sort of surreal moment. Okay, I'll almost finish off with this picture, but these are some other people I met recently in Princeton got us together. And I love this photograph because this was myself, I won it for chemistry, but I got to have my photograph taken with Suki Manabe, who is Japanese, but he's at Princeton. He won the physics prize. And Maria Reza, who's over in the Philippines, and she won the Peace Prize. And both of these people are just incredible, incredible human beings. And for me to get a chance to actually be with them was really great. And one of the things I loved was my family and my daughters got to hang out with them as well. And afterwards, my youngest daughter was so excited because she said to me, you know, Dad, it was just amazing. I actually got to meet Nobel Prize winners. And I was like, well, what am I? Anyway, I thought that was pretty funny. I'll finish off. I always like to thank my family. I've been so fortunate to have incredible family. My wife was born in Korea, grew up in Manhattan. Our kids, we've traveled the world basically on the back of science through invitations. And my wife is actually a fantastic scientist. She actually has helped put 2 drugs on the market. And I always tell people she's the real deal in our family, but I'm so fortunate to have them. And then lastly, one of the things that I did, and I'm very proud of this with my wife, all the money we received from the Nobel Prize, which was just over $500,000, and all the honorariums that we're making this year, we actually have created a new foundation. And this foundation is basically all the money is going to go to help underprivileged kids find their way to college or university. We're big proponents of providing opportunities, and we're very excited to do that. Thank you so much. I'm pretty sure I went too long because I talked too much. But if there's any questions, I would love to chat with you about any of them. And I just want to thank you. Thank you for all your attention.
Thank you so much, Professor MacMillan, for this fascinating, inspirational, and fun lecture. So I'm pretty sure our audience would be thrilled if you could answer some questions. Sure. But before I call the first student to the camera, I would like to remind and encourage the audience to type your questions in the chat box. Now, Henrik, please introduce yourself and ask your questions.
Hi, I'm Henrik Ritter from Beechwood High School in Cleveland, and thank you much for doing this. My first question is, in your expert opinion, in which sector of modern society will catalysis continue to have a big impact?
Oh, I think all sectors, it's going to continue and only going to increase. But the ones which are the most important are sustainability and climate. And I think sometimes people conflate those 2 areas, but they're actually quite different. One of them impacts the other one. But we have to, for climate, we have to come up with catalytic ways to basically either capture CO2 or use electrons to reduce CO2. And that's going to be an enormous, enormous area for the next couple of decades. At the same time, sustainability, we have to move all of the ways in which we perform processes towards more and more sustainable ways, or we're going to run out of the types of catalysts that we need for going forwards and materials that we need for going forward. So those are absolutely going to be the two biggest areas. I mean, medicines are always going to be important. Medicines don't quite have the scale, which is going to have the impact, which sustainability broadly and climate will have broadly. But obviously, medicine is extraordinarily important for our welfare if we're going to also be able to enjoy the planet as we move forward.
So my second question is, what do we say to high schools out there who are deterred from going into chemistry by bad grades?
Deterred by bad grades? Well, that would have been me at some point. It's funny, I have exactly this conversation with my 16-year-old daughter all the time, who's just having the hardest time in the world with chemistry. And I feel really bad for her. Her high school teacher actually now calls me up to apologize. I'm like, it's not your fault, trust me. You know, high schools and grades, it's kind of nuts if you think about it sometimes. We need these grades to sort of get us sometimes where we want to get to. But ultimately, a lot of these subject matters at that point don't reflect what it becomes downstream. So the one thing I would say to people is, you know, persevere, push through. I mean, failure is not a bad thing. Failure is just another word for experience, to be completely honest. And if you push your way through, you will find things where you will find a natural ability or a natural agility towards, because your brain will sort of align with it and you'll find a passion for it. And what you kind of have to do is sample lots of things. One of the things which is fantastic about America is that the college system here lets you try lots and lots of different things, and you can sample it and you can figure out what works for you. So everyone's going to hit bad grades at some point, and I'm okay with that. But I think the key thing is keeping the faith that you're going to get to that subjects, or those subjects where you're just going to be so jazzed about it that you're really going to click with it, and the whole thing is going to allow you to sort of surf your way through.
Thank you.
Now, Kyler Zhou.
Hi, my name is Kyler Zhou. I'm a junior at Princeton Day School. Firstly, I want to say thank you so much for coming to speak to us at ACE. And for me personally, got my AP Chem test coming up in a few weeks. And it's always great to meet a fellow Manchester United fan. So my question is, what advice do you have for future generations of students interested in using STEM to create innovation and change?
Yeah, I mean, it's pretty similar. Number one, find your passion, find what you care about, and sort of find your gravity towards that. Don't get turned off too easily by the initial, it's a bit like saying if you read a book and you don't like the first 3 pages of a book, so you give up on the whole story. And sometimes you have to go 2 chapters in before it clicks, right? And so I always say, sample things, but make sure you give it a pretty good shot. Make sure you know you like it or you don't like it. So that part is really good. But the other part is trying to find for yourself what it is that you want to accomplish for yourself. What do you want to do? What do you want to get from innovations in science? And what is the part of the world that your conscience makes you care about the most? And that's always a really, really nice thing when you can sort of go to sleep at night feeling like what you're doing is having an impact and you're sort of helping your fellow humans around the world. And I think that's what scientists and engineers, that's what we do. I mean, that's literally what we do every day. We have this impact, this really positive impact on everyone else. So that's a really nice thing about defining for yourself what you really care about, so that whenever you do that, you feel really good about it, because then it's no longer a job, then it's a passion.
Thank you so much.
Now, Sean Wu.
Hello, Professor MacMillan. I'm Sean Wu from the Lawrence Welk School of New Jersey. First of all, thank you so much for your amazing and humorous talk. It was very inspiring, and also it's truly an honor to be presenting my questions. So my question is, first, looking back, what are some major decisions, if not the most important decisions, that has led you down this career and to your success?
Well, yeah, I mean, I think I probably talked about one of them already, which was this business. When I went to college, I was told to do physics, and everyone's expectation was you have to do physics because that's what your brother did and it worked for him. So you have to do that. And at some point I realized I really didn't like physics. And so I had to stand up for myself a little bit and make a decision that I wanted to go in a different direction, because I felt, that was the right thing to do. So I think I'm a sort of weird combination of 2 sort of what seem like different traits. One trait is I feel like I'm a very independent person. I like to do the things that I want to do. But at the same time, I'm I'm incredibly respectful person. I really care enormously about my elders. Growing up, really felt, it's a very big quality in Scotland that you really do care about your elders and you listen to them. These are people who have amazing pieces of advice and experience. But the key part was like knowing that you should listen to all of that, but then decide for yourself how you want to use that information. Not that you have to do what your elders tell you to do, but really gain as much of that information from them as possible, such that you as an independent human being can take that and decide for you what makes the most sense. So I would say that decisions for me are really always been about being independent and sort of making sure I follow my own path, but making sure I talk to lots of people to get lots of good advice.
Thank you very much. And do you think you've had any perhaps regrets in your life?
Any regrets in my life? I don't really. Someone asked me that the other day, and I had a really hard time. I mean, they're really sort of minimal things like. I had a chance to go and see a soccer game once, and I didn't go see it, and they ended up in a great, small, tiny things. But for the most part, I've always felt like, having regrets is, not that valuable. You can realize that things didn't go your way and use that as an experience, but don't dwell on it, because if you dwell on it, you're sort of living in the past. And I think what you really want to do is just keep remembering, like, every day is a great day. Moving forward is fun, and seeing where tomorrow's going to take you. So just keep, learn from mistakes, but don't get too remorseful about them.
So I would like to thank the students for their thoughtful questions and thank Professor MacMillan for his insightful answers and, importantly, his encouragement of the students. Now, we have received several additional questions in the chat box from the live audience. And so, Professor MacMillan, would you mind kindly answering maybe 2 questions from the audience?
Sure. These are in the chat box or the Q&A?
These are from the chat box.
The chat box. Sorry,
Yes.
I'm in the wrong place. As usual, I'm in the wrong place. All right.
Hello, Professor MacMillan.
Hi.
Hi, I'm Aditya. I'm a postdoc at Princeton University.
Oh, we seem to have lost your audio. You're on mute.
You need to unmute.
Sorry about that. Yeah. During your talk, you touched upon the importance of different renewable catalysis methods and how they are going to be important going into the future. So my question is, what are the main hurdles stopping that happening sooner rather than later?
Well, honestly, it's knowledge. I mean, knowledge is the problem. We always feel, I think, that we know so much right now. And I would argue in the sciences and in chemistry in particular, we've just really scratched the surface. And what we have to do is understand so much more clearly ways in which we can get molecules that are recyclable to do the things that other molecules can do, but those molecules are not recyclable. So we're trying to transfer the properties of one over to the other one. And to do that, we have to do it from learning a lot and then designing and inventing. And so that's fantastic, right? Because that just gives you so many opportunities of things that we can do in the future. So that's the major hurdle, is taking the things that can do what we want, but are not going to be sustainable or useful in the future, and getting the molecules that can't do that right now and figuring out the ways to make those molecules do that. That's what's going to be critical.
Thanks, Aditya and Professor MacMillan. The one question from the chat box, which I will read out, is, dear Professor MacMillan, what's your advice for junior faculty who want to have a successful academic career in the US?
Wow, that's a really hard question, but I'll give a piece of advice that was given to me. And it's not mine, it's not original, but I really love this piece of advice. And it was from a very successful professor at Caltech, and his name was Dennis Doherty. And he told me the following. He said that, it's really interesting. Success, I mean, the first level of success is getting tenure, right? Being able to hold your job for the rest of your life. And to get that success, he said, to get tenure, he said, people always think you should do A or do B. He said, if you look carefully, there's really 1,000 different ways of getting tenure. And that seems like a very simple piece of advice, but what that's really saying is that everyone has to sort of figure out their own way of making themselves successful, because they have to make it work with who they are. And another way of looking at that is to say, you might watch other people being successful and think, well, I'll just do kind of what they're doing. But the problem is that they're doing that because that's what they're good at. The pathway they've chosen fits with who they are. And at some point, I think as an assistant professor, you have to figure out, I am me, and I have to figure out the pathway that works for me and do it my way. And if you do that, I think you're so much more likely to be successful, because you'll differentiate yourself from other people, but you'll also have a really good time doing it because you're sort of following your own instincts, which I think is the key message in all of that.
Thank you so much again, Professor MacMillan, for your engaging replies to our audience questions. I would like to now ask Xian Tan, an early career board member of AAASE, to present our plaque of appreciation to Professor MacMillan.
Good evening, everyone. I hope you all enjoy this talk as much as I did. I really thought it was lively, fun, and informative, even for someone who doesn't know chemistry like me. So on behalf of the Asian American Academy of Science and Engineering, I'd like to present this plaque to you for your invaluable contribution to this distinguished lecture series. And shortly after, I'll also mail this token of appreciation to you if you could provide the address. So thank you so much, Dr. MacMillan.
Thank you. That's fantastic. I really appreciate that.
So on behalf of AAASE, I would like to thank again Professor MacMillan, Congressman Kim, Dr. Xu, all of our co-sponsors, guests, panelists, and of course the audience for participating in our webinar. In addition, I would like to acknowledge Professor John Wang, Lucien Zhao, and Aditya Lele, who devoted their time and efforts to organize this event and ensure it's the success that we've experienced today. So please join me in giving them all a round of live and virtual applause. So finally, I would like to announce the AACE Summer Academy. This event will bring together students who aspire to careers in science and engineering to meet leaders in a wide variety of STEM fields. The AACE Summer Academy will be an exciting opportunity to network, receive mentorship, and importantly, have fun. This is an incredibly amazing time to develop a career in STEM, so please check out our flyer and the AACE website. I thank all of you and wish you good night.